The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. My name is Drew Burns, and I am the Executive Director of the Slag Cement Association. I'd like to welcome you to today's webinar, Evaluation of Ultra-High Performance Concrete Mix Designs for Use in Bridge Connections and Repair. We're glad you could join us. Attendees are in listen-only mode. You may ask questions during the presentation using the dialog box in the GoToWebinar software. Our speaker will be happy to address questions at the end of the presentation. The ideas expressed in the following presentation are those of the speaker and do not necessarily reflect the views of the Slag Cement Association or its committees. As with all concrete mixtures, trial batches should be performed to verify concrete properties. Results may vary due to a variety of circumstances, including temperature and mixture components, among other things. You should consult your slag cement professional for assistance. Nothing contained herein shall be considered or construed as a warranty or guarantee, either expressed or implied, including any warranty of fitness for a particular purpose. The description for today's webinar is shown on the screen and is also listed on the SCA website with the webinar series information. And now I'd like to introduce today's speaker. Trevor Looney received his Bachelor of Science degree with summa cum laude honors and his Master of Science degree, both in civil engineering, from Missouri University of Science and Technology in 2010 and 2012, respectively. Looney worked towards his master's degree under Dr. Jeffrey Boltz on the effects of bond strength of high-volume fly ash concrete and self-consolidating concrete for infrastructure applications. He is currently working towards his doctoral degree under the guidance of Dr. Boltz, concentrating on the optimization of ultra-high performance concrete for strength, durability, and structural applications, as well as developing its multi-axial tensile failure criteria. And now I'll hand things off to Trevor.
Thank you, Drew. Appreciate the introduction. As I said, my name is Trevor Looney. I'm at the University of Oklahoma. And today I'll talk to you about the evaluation of ultra-performance concrete mix designs for use in bridge connections and repairs. This was part of a multiple-year project with the university, or with between the University of Oklahoma and the Oklahoma Department of Transportation, where they were interested in developing UHPC to do the properties that you saw, and it's been proven to be very effective material. So next slide. First, I'll talk to you about the project scope, because it was a very large project, and then our mix development process and mechanical properties that we tested for. Then we looked into abrasion resistance and concrete bond strength as well. And then lastly, we did some full-scale beam joint testing to verify its ability to replace or be a joint material for bridge decks in Oklahoma. Next slide. So the first step for this was to develop the actual ultra-performance concrete, or UHPC, mix design. And to make it mostly cheaper and easier for ODOT, we tried to use locally available materials wherever possible. We started out trying to get everything locally, but unfortunately, a lot of the materials that go into UHPC aren't actually produced in Oklahoma, so we did have to go out of state for a number of things, but we tried to pick places that was easier to ship from, or things that were readily available. And then for that, the characterization, we did compressive strength, modulus of rupture, and modulus of elasticity, just typical properties that you would need in design and understanding of UHPC. Then, because the intent was to use this as a bridge repair, we tested some other properties that were very important for repairs, mainly concrete bond, how well it would bond to existing concrete, as well as abrasion resistance, since there may be instances where it's used as a roadway surface or anything like that, and we wanted to make sure that it could perform as well as some of the other materials that are available. And then lastly, we did the large scale slab tests, which they were mimicked after Abrasion, Oklahoma, and we actually created these 8-foot slabs that we connected and tested under a single point load. Next slide. So as I said, local materials whenever we could, and unfortunately we weren't able to, but the mix development process took about 1.5 years total. We went through a number of different mix designs, but we used mainly type 1 and 3 cements. The supplementary cementitious materials we focused on were fly ash, slag cement, silica fume, and vitrified calcium aluminosilicate. It's a product that Vitra Minerals produces. Very similar to slag cement. It's more since it's produced, it's more the gradation's more even, as well as chemical composition. We use fine masonry sand, very similar to most other UHPC mixes, high range water reducer, and commercially available steel fibers. We started the process looking at some already published mix designs from the FHWA. We figured that'd be a good starting point, and maybe if we got lucky, then the materials we were using would produce similar results, and we would only have to do some fine tweaking. But unfortunately, it didn't work that way. We found that a lot of the mix designs that we mimicked didn't actually get the same properties as the FHWA had published, and figuring there could be any number of reasons, we decided to go ahead and branch out and look around using different materials and different mix designs and trying to find out what that best combination would be. But our next step was looking at particle packing, which particle packing, it's pretty common in UHPC mix design. The idea is to reduce the amount of free airspace inside of a mix. So you fill it with various sizes of grains from the different materials that you use. And because UHPC has such a low water to cement ratio, you actually use the cementitious materials in that particle packing as well, because not all of the cementitious materials are hydrated. Some of them remain dry, and they actually become kind of a pseudo aggregate inside of the mix. So when we went through that, a lot of the published research at the time showed that the particle packing was a very important, arguably the most important thing with UHPC outside of the water cement ratio to give it the strength and durability that it has. But one thing we found was that our particle packing study didn't actually increase the strength much above some of our other studies that we did, just changing the cement types and things like that. So it didn't seem to have as much of an effect. So after we did that, then we started to hone in on different SCMs, just like slag cement, and maybe thought maybe the reactivity is the bigger issue, and that maybe our local cements don't quite react the same way, which would indicate that would be why our FHWA mimic designs didn't actually turn out the way they were supposed to. And when we started adjusting our SCMs a little different, we started to get higher strengths, and we ended up seeing that the reactivity was really the main driver for our mix designs and what gave it its strength, not so much the particle packing itself. Next slide. So I bring this slide up mainly because in our mix design, some of the materials we use are slightly different. On the left, you see the fibers that we used, and you'll notice the most common fibers that are used inside of UHPC are kind of hair-like. They're Dramix fibers from Becker. They're 1/2 inch long, 0.2 millimeter diameter, little hairs. I call them little hypodermic needles when you get them in UHPC. But because of the expense, and we were trying to really reduce the cost of our mix, we decided to go with a cheaper fiber, and we ended up using these. Are about 1 inch long. They're meant for reactive concrete, but or refractory concrete. But their weight did cause us some problems because they are much heavier than the Dramix. So we ended up having to adjust our high range a little differently, so that way we could maintain a flowable mix without them and maintain suspension of those fibers, as opposed to adding too much high range and then having them all sink. And then the other slight difference, although it's become a common as it's gone along, we used masonry sand, and if you look at it, it looks more like a clay sand, or it looks more like a paper sand. This was actually just a readily available sand locally in Norman, Oklahoma, where our school is, and There's really not a whole lot special about it outside of the fact that it doesn't have very large particles. I think the highest particle size that we've had in this is 1 millimeter. But the typical UHPC mixes will use a sand similar to this, but they will also use like a quartz flour or something that's super fine. And we avoided using that mainly just for the expense, because those materials are very expensive, and it's best to avoid those if you're worried about cost. So next slide. And we went through a bunch of series. We labeled them by letters, series A all the way up to J. And series A started out with the mixes from FHWA, and then through all of our reactivity studies and our particle packing and looking at all of our different SCMs, we got to series J, where we combined all the promising things that we saw into a bunch of mixes, and then we narrowed it down to these three to characterize. So J8 is the only one that uses the VCAS. It's sort of something similar to slag cement, which is much more expensive. And then J3 and J13 were the two we picked, and they actually had the most slag cement. So one thing we found when we started using slag cement in our mixes was that we were able to reduce the amount of silica fume we use. If you notice, our silica fume is actually really low. I think it's about 10% of the cementitious is silica fume, which is lower than typical UHPC mixes. And we replaced it more or less with slag cement. The silica fume, because it is such a fine particle, it tends to make UHPC super sticky, and it's really hard to work with. So it becomes a problem if you add too much silica fume, because conversely, the silica fume also gives its density and its increased durability properties, increased strength properties. So you gotta be careful when you start reducing the silica fume. But if you replace it with slag cement, we found that you actually do regain most of those benefits, the compressor strength and the durability. So we tried to just max it out as best we could, and we ended up picking replacement levels of 30 and 40% of the cementitious for slag cement. We actually got ours from Lafarge Holcim out of their South Chicago plant. And you can see our water cement ratio is 0.2, something we picked early on. And then the type 1 cement is used about 60%. And then on J13, the type 1 and 3 is total 60%. So next slide. The J3 was the one we seem to get we'll say the best workability versus strength to work with. So J3 was the one we decided to use for some of our bigger scale testing and our bond testing, because while we wanted strength and it wasn't necessarily the strongest mix that we had, it did have the best workability while maintaining a high level of strength. And workability in repairs is very important, especially when you use UHPC, because you want to, the benefit of using UHPC is its strength, and because it's so strong, you can use much smaller repairs and much smaller joints. And because they're so small and they can be congested, you need a highly flowable mix to actually get to all those recesses. So J3 struck that balance between workability and strength that we were looking for. So we went ahead and did most of our testing, big scale testing with that. Next slide. So as I mentioned before, the properties we tested were typical characterization properties: compressor strengths, modulus for rupture, and modulus of elasticity. One thing that is pretty common with UHPC is heat curing. If you heat cure it, you tend to get slightly higher strength. So we decided to do compressive testing heat cured to see how well it compared. We also adjusted the level of heat curing, because at the time there was no ASTM available for UHPC. So we were trying to come up with our own heat curing regimes that we could give to the ODOT. And we looked at different heat curing methods, and one of the best ways we saw was putting them in an oven in a little tray that's filled about halfway with water, so it sort of mimics steam curing. We got it up to about 180 degrees Fahrenheit, and we cured it for various amounts of times. And then for the fiber content, we only did compression and MOR with fibers as well as without, and then the modulus of rupture we only did, or the modulus of elasticity we only did without fibers. Next slide.
Hey, Trevor, really quick, we got one question that came in that what are the dimensions of the fibers that you were working with?
They were about, I forget the diameter, but they were 1 inch long, and they had an aspect ratio, I believe 46. I want to say it was about 0.2 inches, 0.1 inch. But the one thing to note about those, and this was something that caused us no end of trouble because we really had to fight with the high range, was they were heavier than the Dramix fibers. So we did a lot of looking into how to optimize the flowability and without compromising the way they float and making them sink, because that is a big issue with UHPC in general. Is you want higher flowability because it's obviously going to flow much better through these congested areas that you want to use them for. But the higher flowability you have, the less likely, even with the Dramix fibers, the less likely you are to keep them suspended. So you end up with a lot of segregation. I've even seen that with the Dramix fibers that we've used in our lab. Start getting above 10.5 inch flow, they don't tend to stay suspended, which becomes a problem. So the as I mentioned, the compressor strength was tested at different heat curing times. The temperature was the same, and they all had about the same amount of water in those little tubs. One thing we noticed that 36 hours was about the best heat curing time for all three concretes that we tested. The one thing we did notice is that heat curing seemed to be much more effective with the steel fibers as opposed to without. And I think that has something to do with the steel fibers being able to radiate the heat inside of the material a lot more effectively as opposed to an unreinforced or no fibers in the UHPC where the heat just has to traverse the cross section to get to the center. Because these fibers, because they tend to touch and collect, they'll send the heat to the inside of the cylinders much faster. So you get some benefit with the heat curing using those fibers. But we also, one thing we did notice, we thought was a little strange, after 36 hours of heat curing at 48 hours, there was a slight drop in the strength, which we thought maybe indicated an upper bound, that if you heat cured it too long, you could start either damaging it or maybe just drying it out or anything like that, which could cause issues either way. So we decided to stick with a 36-hour heat cure for our study, and that was the recommendation we gave to ODOT. Next slide. Our Modulus of rupture results were a little interesting. With our compressive strengths, all the mixes seem to be relatively similar. J3 outperformed them, but not by a whole lot. But the Modulus of rupture, J13 really outperformed everything in bending, which was surprising. And J3 and J8 were relatively similar. But the most interesting thing I'd like to note on this is that when we did reach pretty high levels of Modulus of rupture, even for a UHPC, the first bar on the plot is the first cracking, so it's not even the ultimate strength. It's more or less we wanted to evaluate how much those fibers helped up to cracking, and it didn't seem to help much at all. But the unreinforced Modulus of rupture tests, every single one of them had this really interesting failure crack, in that it started vertical at the bottom where the highest flexural stress, tension stress is going to be, and then as it reached up, they all had a slight curve to about 1/8 of an inch from the top of the specimen, and then a jog back, which we're still not sure what it indicated. It's something that I personally would like to study more, because it looks more like a tearing motion than a typical concrete cracking motion. So it could indicate a potential for increased energy absorption capabilities. We're not sure. It's something that, like I said, I'd really like to study later, but we've had other more pressing projects to work on. Next slide.
All right, a few more questions, Trevor. Sorry, I think they're appropriate as we go instead of waiting till the end. First question, why do a T3 T1 blend instead of 100% T3 as the third option? Most times both cements will not be available for blending at the same time.
Yeah, so I guess that last part of your question, so the part of when we had discussions with ODOT, part of the things was to get all of the materials separately. So it's kind of like given to a ready mix plant, and we were training them on how to basically identify the materials that you needed and mix it yourself. So the blending isn't, it's not necessarily pre-blended like I think you're mentioning, but to your first part, the reason that we tried mixing the amount of different types of cement was we were trying to improve the early age strength to see if maybe supplementing some of that type 1 with type 3, we could get higher. Our threshold at the time was 14 KSI. We were hoping to get 14 KSI in 3 days or less. And it was pretty difficult with only type 1. We were only getting up to about 11 or 12. And 14 KSI was the limit ODOT wanted to reach. So when we started putting type 3 in there, we were able to get closer, but it didn't have as much of a benefit as we had hoped in getting that early age strength. But the late age strength was still very similar to J3, where it was all type 1.
Okay, and other question, how was the fiber distribution in the concrete mix? Did you get balling?
No, oddly enough, I expected to, because we're around 2% fibers, which is a pretty common percentage. It's what Ductal uses. Ductal is a Lafarge-Folsom product. It's basically the gold standard for UHPC. But in any of our tests, and I actually cut a few cylinders open to see if we could see anything, we didn't notice any balling. That might be due to the fact that we don't typically use a pan drum mixer. It's a high shear mixture is usually required with UHPC to mix it fast enough. Otherwise, your heat gain gets too crazy. But the high shear mixture does a number on really pushing the fibers around and making sure that they don't ball up like you're mentioning. So, yeah, I fortunately we hadn't noticed anything in any of our tests.
Okay, and one more question before we keep going. What is VCAS? Is it similar to silica fume?
It's more similar to slag, but it's a manufactured product where slag is a recycled product just from making steel. But the VCAS is something I forget what it's made out of. Probably some level of silicates and clays, and they sort of make it similar to cement and blend it and get the gradation that they want. But I think because it is manufactured, I noticed it didn't seem to react as well, which is why J8 didn't seem to have it was we'll say the lowest performing more or less, in my opinion, than the other mixes. But because it was a manufactured product, I don't think it blended well or mixed well with everything that we use, the cements as well. Is that it?
Yep, that was it. Let me know if you need me to go ahead one more slide or if that's good.
Nope, this is perfect. I'll get going. The last characterization we did was the modulus of elasticity, and we compared it to 2 different equations. One, the typical ACI equation for normal weight concrete, and then Russell and Graybill, some of the earlier pioneers of UHPC, they developed a relationship similar to the one for normal strength concrete for UHPC, and you'll notice it's a smaller multiplier, which that's pretty typical when you start looking at higher strength concretes, is that the relationships between them become a little less exaggerated, in that you don't always get 10% tension strength out of a UHPC at a higher strength than you would in a normal weight concrete, which would be really awesome if you get 10% of 22 KSI for tension strength, but unfortunately that's not the case. So they adjusted that multiplier, and one thing we found was that adjustment worked really well with our mixes. We are actually at our farthest, we were still less than 10% different than the Russell and Graybill equation with all of our tests. So I think it's a pretty good equation to use. And I know last I heard, FHWA was creating a specification for UHPC, and I hope they put that number in there because it seemed to work really well with ours. But as expected, the ACI equation over-exaggerated the stiffness based on the compressive strength. Next slide. Then we did abrasion tests just to verify that it is a more dense material. UHPC is known for having very few voids and being very dense at a microstructure level. But this is an additional test just to clarify that it will be a lot better than normal strength. But this brings us to what we tried to compare to in some of these more in-service tests, we try to compare it to Ductal, the Lafarge-Folsom UHPC. As I mentioned, it's the gold standard for UHPC. It outperforms most. And it's been studied for decades. I think it's been around since around the early to mid 90s. So there's a lot of research and development that went into that mix, and so we chose it to compare ours to see if we could get even close to that, then it must be a good mix. But as you can see, on the form surface for the abrasion, our mass loss was much higher than Ductal. But J3 and J13 performed very similarly. It's probably because the slag cement tended to make up for the silica fume better than the VCAS did in J8. But so one thing to note, and I think is maybe a slight benefit for our mixes, was the trowel surface, which is just the open surface on the top, was a lot more bubbly with Ductal than it is with our mixes. And there's something about Ductal that causes a lot of the free airspace inside of the mix while it cures to come to the surface, so that you get this friable surface at the top. So that's why Ductal has a requirement for their mixes, in that you have to grind off the first, I believe it's a 1/4 inch, maybe 3/8 of an inch. So whenever you pour it, you have to pour it high and then grind that top surface off, because you get all those extra air bubbles up there. And we didn't seem to have that in our mixes for whatever reason, which is why it appears that our trowel surfaces perform so much better than Ductal. But that's mainly because we didn't grind the top surface. We just tried to keep it apples to apples. But if we were to grind the top surface, you would have the same level of performance with the Ductal and the trowel surface as you did on the form surface, which would make sense. But as you can see, the J8 seemed to perform the worst. But even so, with all of these abrasion tests, we had super low mass loss on all of them. Less than 4 grams, even with our highest J8. Next slide. And then the last of what I call small scale tests is we did the concrete bond strength tests. We did a typical, it's a mimic on the modulus of rupture test, where we cast 1/2 with conventional concrete, let it cure for at least 28 days, and then we would pour UHPC against it. And we varied the angle of the interface as well as the surface condition of the interface. On the upper left of this, we did a exposed aggregate finish. We put a retarder on the form surface and sprayed it off to get some of that paste. And then we also did sandblasted, unclean, or just cut, and then wire brushed. So after pouring them and letting the UHPC cure for 28 days in ambient conditions, we tested those in 3rd point bending, similar to the flexible test. Next slide. One thing to notice, Ductals performed very well in all of the tests. One thing we noticed, we only had one of the Ductal specimens out of all of the tests that we did. We only had one that actually failed at the interface, and even it failed at a level that was similar to the monolithic modulus of rupture of the normal strength concrete. But the rest of them failed in the normal strength concrete, showing very good bond. And for the J3 that we tested, it was the bond angles that were best were 45 and 60 degrees. They performed very similar to the Ductal, even though they did fail at the interface. But one thing we noticed, that while they failed at the interface, they were very similar to the monolithic strength of just the conventional concrete. So we counted that as a win. It would make sense that the weak surface would be the interface. All of the aggregate conditions, or the interface conditions, showed that, but except for the shear key, which we did the exposed aggregate on. All of the exposed aggregate conditions tend to be much, much lower for J3 than they were for Ductal. And they all failed at the interface. We believe it's potentially twofold reason. One, while Ductal is a proprietary blend, we're fairly certain it does have more silica fume, because most UHPC mixes that you'll see will have anywhere from 15 to 25 or 30% of the cement or the cementitious is silica fume, which is really mainly to increase the the density and the durability and the strength. Well, we lowered our silica fume to improve our workability, but I think there's potential that the silica fume may increase that bond strength because it is such a fine particle. It's so small, it's more likely to get into the crevices and the pores of conventional concrete. So I think it improves the bond strength. But mainly, one thing we observed was all of these mixes have a very low water cement ratio, and J3 seemed to be susceptible to moisture migration at the interface. None of those interfaces were treated with water, they were just dry. We were trying to do a worst case to see what we were working with. And we noticed that it looked like the exposed aggregate interface just seemed to suck the water right out of J3. So it would break at that surface and we would actually see dust right at that interface on the surface of the UHPC. It really indicates that it's very important to maintain an SSD condition when bonding UHPC, especially J3, and it's mainly due to the lower water cement ratio. There's not as much, really any free water floating around in UHPC, so whenever it comes into a contact with a dry concrete surface, it's going to suck whatever moisture it can out of it, and so the SSD condition will reduce that dramatically. So we found that SSD is really important for J3. Next slide.
A few more questions, Trevor. Does ODOT have UHPC section in their specs, and were you able to meet or exceed them in terms of mechanical and durability?
No, the UHPC specs were actually developed and was part of this project. This was all new to them when we started. It was around 2017. So they didn't have any specs, but one thing we did note was that we had issues reaching that at 21.7 KSI compressive strength. No matter how we put it, no matter what mix design we used, it was really tough to hit that. So we're starting to think it might be some of our local cements. They don't seem to react as well at low water cement ratios as others. So I think because of that, their specifications are going to be a little lower for UHPC and compressive strength. And I'll bring this up later, but we did notice that the compressive strength didn't really affect some of the important properties as much as we would have thought. But I'm pretty sure the FHWA was also considering lowering that compressive strength, because I don't think ours was a unique problem, and that a lot of studies using these locally available materials had issues reaching those high strengths. And I think it has a lot to do with the cements that are locally available. It all just depends on where you are in the United States.
I think you touched on this quickly, but what is Ductal?
Ductal is it's a proprietary UHPC by Lafarge Folsom. I've studied it quite a bit early on. I believe they started making it, or it was initially a French company back in the mid-90s, I believe. They started publishing papers on it, looking more into these ultra-low water cement ratios, taking out the coarse aggregate, particle packing models, things like that. And eventually evolved into Ductal. And it's been commercially available for a good 2 decades, I believe. It's been used in a lot of projects. It's most commonly used in projects now, mainly because it's been tested so much and proven that it works. You get UHPC properties all the time using this product. So FHWA and a lot of state DOTs love to use it. The unfortunate side of that, and mainly because it is so good, is the cost. It's a little more expensive to use Ductal than it would be to use something like we're creating. So that's about the only hang up DOTs have with using it, is just the initial cost. But when using UHPC, even our mix gets really expensive. It's I believe around $700 a cubic yard. You gotta outweigh the initial cost with the benefits of not having to repair it every 10 or 15 years, because this stuff holds up really well in harsh environments.
All right, and lastly, before we go on, did you use any defoamer, and did you measure fresh air content?
Did you say defoamer?
Yeah.
No, that's mainly the reason I believe that we didn't have the bubbles rising to the surface. We avoided using that just for cost, but we didn't do air content. Although that would have been a good number to have as to compare to Ductal, because we obviously would have a much more porous structure than Ductal would have. Is that all?
Is it for now?
Perfect. lastly was our slab joint test, which I thought was the most fun. What we did was we modeled slabs similar off of a bridge somewhere in Oklahoma. I'm not even going to try to pronounce the name. The bridge was discontinued after a time, but it's they chose it because it was a pretty common design that they used. So we actually got a hold of some of those bridge decks, and we just modeled after them what our deck design was going to be. And we would cast these 4x4 decks with some bars sticking out. And the bars stuck out about 5 inches or 8 inches or so. And then we would tie them together with a very short lat bar in the center, as you can see in the upper right. This equates to approximately an 8 dB splice length, which is a common recommendation for ductal UHPC because it has such high strength, and the addition of steel fibers helps really increase the bond strength and really reduce that development length. So to test it out for ours, we went ahead and ran with that 8 dB limit. We tested slabs with both ductal and J3 as the joint material. And as you can see on the bottom right, to mimic the heat curing, we put a heat lamp over top of it and then covered everything in plastic immediately after casting because of the low water cement ratios, it's really easy to lose water to evaporation on the surface. You get a desiccated surface. We did that to hit our strengths quicker. We did our cylinders as well to track that strength. So next slide. This is our slab setup. So the two together, about an 8-foot span. The joint is about 12 inches wide. And then we applied the load through what was meant to recreate a wheel load just to the side of the joint. And as you can probably tell with this picture, that ductal is poured just ever so slightly higher per the recommendations. We didn't grind anything off, we just kept it that way. But we also poured J3 similarly just to try to maintain similarities. But the load was put just to the side of the joint to help maximize the load that would be applied in that at the joint interface. And then we did both static tests where we just applied the load until failure. We did 2 slabs of static tests for both materials, and then we did 1 dynamic test where we did about 1 hertz cyclic loading for 3 million cycles. And then it was at a load that was just below the cracking load. And then we increased the load to just above the cracking load and took it until it reached a 3/4 inch failure or a 3/4 inch deflection limit. And then after that deflection limit, we tested that slab to failure under static load. Next slide. Here's a picture of one of the slabs post static load, I believe. You can see there's a nice crack that goes along the top surface, showing that we did fail some of the normal concrete and compression. But one thing we did notice is that all of the failures occurred in the normal strength concrete. We actually didn't see any cracks in any of the UHPC, which I thought was phenomenal. There was a little bit of joint separation. Next slide. That we did see later on. Here's another view of that. And then next slide. This is a close-up of that joint. You notice on the left there is a joint separation, which we kind of equated that to bar yielding and in a lot of cases bar rupture. But the main crack happened directly over the load point in the normal strength concrete. And like I said, we didn't see any cracks in the UHPC, which we thought was great. Next slide. This is a plot of all of the static tests that we did on ductal. The first 2 big ones are the regular slabs where we didn't do any cyclic loading before. That calculated failure load was the estimated failure load for just a monolithic conventional concrete slab. So we did exceed the strength in all of those, which is great. And we did reach we got a lot of ductility out of the ductal slabs. And then the cyclically loaded test was that bottom little plot. It obviously didn't reach as high as the unloaded slabs, but you did get a little bit. I was a little surprised at the ductility we got out of that. I presumed it would have just popped because we took it, I believe, up to 5 million cycles even after increasing the load. Next slide. And in this one, this is for J3. You'll notice we didn't get quite as good ductility as we had, but we did still exceed the monolithic slab strength, which in my opinion was the most important. And the overall failure loads were slightly lower. But we even with the fatigue test, the cyclic loaded test, we did have a lot of ductility in that, just like Ductal did, which I thought was great. But one thing to note about all of these tests, which really surprised me, was we had at least one rebar rupture in every single slab that we tested, which shocked me because with the shortened development length that we used, and we only had 5 inches of bar or so embedded in that concrete. Even with J3, which was noticeably weaker, I believe it only got up to about 19 KSI, I believe. In Ductal, that slab got up to about 23 KSI. But even at that lower strength, we were still able to fully engage the bars with that shortened development length, which I think shows that mainly just because of the way it flows, because it flows very well. If you've ever seen UHPC, it kind of flows like putty that just never stops, and it tends to wrap around things very easily. And then the steel fibers were able to help monitor or help mitigate those micro cracks that you'll get once you start putting concrete in tension. And I think all of that combined really improved the bond behavior, even with a lower compressive strength. And so I think it's a good sign. It may show that while compressive strength is really nice to have in a lot of applications, whenever you're looking at bond strength or using shortened development lengths or really small areas for repair, you don't have to demolish near as much and still get developed rebar from a smaller section, even with a smaller compressive strength like you see with J3. Next slide. And this plot is based on it's the stiffness. Each dot represents the stiffness of the middle of the day during the cyclic test. So what we would do is we would download the data from the cyclic loading, and we get the slope of a certain amount of time in the middle of the day. We'd average it all, and then it would give us the stiffness value for that day. We plotted both J3 and Ductal, and we noticed that for the most part, they perform very similarly. And this is the misfortune, I think, in this test. And these tests take about 3 months to run. So it was unfortunately, it wasn't something that we could easily redo. But around day 20, we had an error in our MTS pump that we use that operates the ram. And unfortunately, that error caused the ram to immediately apply, I believe it's 16 kip load, which was about twice as much as what the cyclic load was supposed to be. And because of that, it initiated additional cracks. And that's why that dip in the J3 stiffness plot, that's what caused that, was just that error prematurely cracked the J3 slab, which lowered the stiffness. But at around day 35, 36 is where the 3 million cycles at the just below cracking load occurred. And so we increased the load. As soon as we increased the load on the ductal slab, you see that it goes to about the same level as J3, which sort of shows that had we not, at least what I think, had we not previously damaged the J3 slab in the middle of the test, it would have been a very similar trend as Ductal had, which I thought was great. But one good thing is post that we did fall within the FHWA limits for fatigue failure once we increased the load, and Ductal actually extended that quite a bit farther for a couple of days. But well, I was very happy with the fact that even though our compressive strength was much lower and therefore our stiffness was much lower of the material itself, in terms of overall behavior, we were able to maintain a very similar behavior to Ductal as J3. So that was a really promising results. Next slide. I just want to say thank you very much for sitting and listening to me. I could ramble on about UHPC for days. I want to thank the companies listed, specifically the Slagsman Association, for their the generous award. We're really proud to get that and give me the opportunity to do this webinar, and all the companies that donated materials. Lafarge Holcim has been very helpful. It's been these materials can get kind of expensive and they're a little hard to get sometimes, so they've been very helpful in getting all that. But if you have any more questions, I'd be happy to answer them.
All right, thanks, Trevor. We do have one more question here. What is included in the 700 USD cubic yard cost? Even fibers?
Yes, that's even fibers. But the one thing I should note is that the fibers, it really depends on which ones you use, because those prices vary wildly. And I believe the more common and arguably the better fiber to use from Becker, those are I believe about $2 a pound. Although they've changed their shipment or they changed their manufacturing processes, so we may not be able to use them at all anymore, or not much longer, because they're no longer manufacture that in the U.S. The fibers we used were about, I want to say $1.75 a pound, but without the fibers account for almost half the cost. They just get so expensive when we use so many of them. Some of the research that we're focusing on now is looking at reducing the number of fibers or the amount of fibers we use to reduce the cost, to see what sort of behavior we get.
All right, that is the last question we have here. I'd like to thank everybody for attending, and we will have these recorded webinars from the series uploaded to our website, hopefully within a few weeks. And it looks like we have one more question that just popped in.
Okay.
Were you able to achieve the FHA objectives as far as the compressive strength at 21.7 KSI?
I always hesitate to answer this question because I have no proof, but I have done it. And it was a random mix. I've done a lot of test batches with this, not really changing anything, just sort of monitoring our materials, or if we switch up. A lot of times when we switch bags of the supplementary cementitious silica fume and the slag, or when we get a new batch of type 1, I'll try different things. I'll try other mixes, but I have actually gotten it. I've gotten J3 to hit about 22 KSI, almost 23 once. But unfortunately, it was never in one that we were closely monitoring. So it's never been in any published studies, but that just goes to show, I think it has a lot to do with just the variability in some of these SCMs that we get. Unfortunately, there's no real big standard. A lot of our material, it's relatively even. I'll say a lot of, between batch to batch, we'll get very similar results. We consistently hit 18 to 19 KSI on our compressive strengths. But every now and then we'll get a couple of good batches where we'll get really higher compressive strengths for any number of reasons.
And one more here. How do polypropylene fibers perform WRT steel fibers in UHPC?
So I've never actually used polypropylene fibers. I haven't seen too many studies that have. I know that people are looking at them. I think the main issue for those would just be overall strength. And then I'm not familiar with WRT fibers, but steel fibers seem to be the most common just for overall strength that you'll get. But one thing we have noticed is that we don't actually get to utilize a lot of that, because these fibers that are typically used are hairs, more or less. They don't have any ridges or deformations, so they don't bond very well. So most of the fibers don't actually rupture. They fail to pull out. I think that was part of the reason why we had such good modulus of rupture results, was the fibers that we used were actually, they had ridges on them, so they bonded a little bit better. They had some mechanical action.
All right. Well, again, thank you, everyone, for attending, and thank you, Trevor, for giving a presentation today. And if you haven't done so already, please check out slagcement.org for more resources on slag cement use in concrete construction. Thank you. Have a good day.
Thank you.